DeepSeek researcher just released a side project that is for faster LLM inference, and it went completely viral. 3.7 thousand stars on GitHub, that's crazy. Goes to show how skilled DeepSeek researchers are. It's similar to VLLM, this is just a smaller version that's made for, it's a bit faster also, but it's made for learning so you can understand the code. The code is a lot simpler and you can understand it. It takes only this code to run it. So let's take a look at the code and understand it. Also, you can see benchmarks here. It actually runs a bit faster than VLLM and has higher throughput tokens per second. And the stars of this GitHub repository are going viral. NanoVLLM is a from-scratch, lightweight implementation of high-throughput LLM inference engine inspired by a popular VLLM library. So it has PagedAttention, a memory management technique that eliminates internal memory fragmentation by storing the key value cache in non-contiguous, fixed-size memory blocks similar to virtual memory pagination in operating systems. Continuous batching. Instead of waiting for all sequences in a batch to finish, the engine processes requests continuously. As soon as a sequence finishes, a new one from the waiting queue is started, maximizing GPU utilization. Prefix caching or KV cache sharing. If multiple requests share the same initial prompt prefix, the computed KV cache for that prefix is shared among them, avoiding redundant computations. This is implemented via hashing, so this is the cache hit. Those ChatGPT and other companies have this reduced pricing on cache hits. Tensor parallelism. For models too large to fit on a single GPU, the model weights and computations are split across multiple GPUs. Yeah, it has that as well. CUDA Graphs and Torch compilations. To reduce the Python overhead in the decoding loop, the model's computation graph is captured and replayed on the GPU, and key components are just-in-time compiled with Torch compile. First, there is this LLM or LLM engine. This is the frontend, the user-facing API. It receives generation requests, creates sequence objects, and sends them to the scheduler. It orchestrates the main generation loop by repeatedly calling step. And then we have scheduler, which is the brains. Block manager, the memory manager, implements the core of PagedAttention. It manages a pool of physical KV cache blocks and handles their allocation, deallocation, and sharing for prefix caching. So if we take a look at the repository, all of this is in this engine, because layers, models, this is just so layers is just architecture, but this engine is what this VLLM is about. So layers is transformer architecture. Here you see attention, embed head, layer, norm, linear, rotary embeddings. And then engine is what we are talking about. Runner, scheduler, sequence, block manager, LLM engine. Then model runner, the worker. This is the component that interfaces directly with the GPU and the PyTorch model. It takes a batch of sequences from the scheduler, prepares the necessary tensors for the model, like input IDs, positions, and block tables, executes the model forward pass, and returns the generated token IDs. It also manages tensor parallelism and CUDA graphs. Then let's go to detailed component breakdown. You see how simple this is. Just install, and then this bit of code, this will completely run. It also prompts, outputs. This is enough, and then it works better than VLLM. And you can see that star history here. It's going kind of viral. So the config py is the config data class that holds all static configurations for the engine, such as model path, batch sizes, memory utilization, and tensor parallelism settings. This is it. So we see a bunch of just stuff in here that I just mentioned, the paths and the settings. and then sampling params pi. Sampling params data class holds per request parameters like temperature and max tokens. Here we can take a look. So data class, temperature, max tokens, ignore end of sentence, or end of sequence, I think this is. Then we have this LLM.py and engine, LLM engine pi. So LLM pi is just a simple wrapper around LLM engine. And if we go here, you can see that in NanoVLLM, LLM, it's just a wrapper around LLM engine. So if we go back, LLM engine is the main entry point. In it, it initializes the scheduler, the model runner, and the tokenizer. So it starts by reading the config file and then initializing here the model runner and then tokenizer. Depending on the model, it's going to automatically initialize the tokenizer. And then the scheduler here as well. If tensor parallel size is more than 1, it spawns multiple model runner processes, one for each GPU, if there is multiple GPUs. If using torch multiprocessing. Communication with these worker processes is handled in the model runner itself. The generate method is the main user-facing function. It adds all prompts to the scheduler, then enters a while not self is finished loop. In each iteration, it calls self step, which runs one forward pass of the model and processes the results. So we have the step function that will run one forward pass and then generate. This is gonna get the prompts, list of prompts, and call step. Yeah. Now let's take a look at the PagedAttention engine core. This is the heart of the system, composed of the scheduler, block manager, and the sequence classes. So NanoVLLM engine/sequence pi. So here in the engine sequence pi, this file is not actually that long. It just has a bunch of functions defined. A sequence object represents a single request's journey through the engine. It stores the token IDs, prompt completion, sampling parameters, and its current status, waiting, running, finished. Crucially, it holds a block table, a list of integer IDs that map the sequence's logical token positions to the physical KV cache blocks managed by the block manager. I guess it just somehow keeps track of which KV cache blocks correspond to which tokens. You can take a look at the sequence class once more. So is finished number completion tokens. It's gonna be number of tokens minus number prompt tokens. Yeah. And then prompt token IDs from beginning to the number prompt tokens. Okay, it's kind of crazy. Yeah, it's interesting. It's simple to understand. Other things are usually not so simple to understand. It's like the prompt tokens are in the beginning of the entire text. It has also generated tokens. So to take prompt tokens, you take the entire text that includes generation as well, and then just go from beginning to the number of prompt tokens. Number cached blocks is gonna be number cached tokens divided by block size. It's so funny because it's so simple to understand, and other things are so tough. Then we have block manager pi. So this manages the KV cache memory, which is divided into fixed number of block objects. So it's just KV cache is divided into blocks. So this function is important, allocate, that takes this sequence. By the way, guys, there is a construction site where I live and they cut a water pipe accidentally, so we had no water. But after like 1 or 2 hours, they fixed it, so now I'm so happy I have water. So allocation, allocate, when a new sequence is scheduled, this method assigns free blocks to it. So free blocks in KV cache. So this is where prefix caching happens. It calculates a hash for each full block of tokens. So I guess sequence is divided into blocks. If another sequence has already computed this exact block of tokens, it finds the block ID via self hash to block ID and reuses it by simply incrementing its reference count, saving a forward pass for that part of the prompt. So instead of calculating a KV cache for this block, if it already exists, maybe user is just continuing to sending more messages. So the conversation is happening over, so the conversation gets sent, but it has already been computed, a lot of it, in the past message. So it will just use this pre-computed in the past message KV cache. Because as I add a new message to the ChatGPT, they don't need to every time pre-compute KV cache for the entire conversation. They can save it and just compute KV cache for the new message that I sent. Then we have this appending, a may append. During the decoding phase, generating one token at a time, this method ensures that a new block is allocated to a sequence before it completely fills its last one. What? I don't get this, guys. If you understand it, then tell me in the comments below. Let's check the allocation. So here, when a sequence is finished or preempted, so it's no longer running, this method decrements the reference count of its blocks. So, you know, as I said, we can have one KV cache block referenced by multiple generations that are running. So, as I said, if the generation is using same prompt in the beginning, for example, first part, then it will use like the same KV cache. It will not recalculate KV cache. So if the number of running sequences that are using this KV cache block drops to 0, then it will be returned to the free pool. So it will be freed out, the memory, the KV cache. Then we have scheduler. The schedule method implements continuous batching. Prefill phase. It first tries to batch new sequences from the waiting queue. It checks if there are enough free blocks a block manager can allocate, and if the total number of tokens in the batch doesn't exceed a limit. Then we have this decode phase. If no new sequences can be prefilled, it creates a batch from the sequences already in the running queue for the next token generation. I'm not sure exactly what this means. Preemption, a key feature for maximum utilization. If a running sequence needs a new block but none are available, block manager can append is false. The scheduler can preempt another running sequence, move it back to the waiting queue, and free its blocks to make space. Okay. So when this thing is running, maybe it's generating some text. If it needs more storage, more blocks in the KV cache, but there is no more storage, this can actually free up storage by canceling running of some sequence and moving it back to the waiting list, waiting queue. I think I understand this decode phase. So after the prefill phase, where they calculate the KV cache of the prompt that was sent, the text that they already have in the prompt, then we go into the coding phase where now the next tokens are generated. And that's after all of these new sequences are pre-filled. Then it groups them into a new batch and starts the next token generation. Then number 3, model execution and parallelism. So in the model runner Pi, we have this tensor parallelism. So the first graphics card, if there are multiple, the rank 0 is a controller, and it writes into shared memory, and the other workers, the other graphic cards, running in their own loop, wait on the event, read from shared memory, and execute the same method. That's KV cache allocation will just calculate the number of blocks that can fit in the specified GPU memory and allocates one large KV cache tensor. Slices of this tensor are then passed to the attention layers of the model. Which slices and how, hopefully we will see later. So prepare prefill and prepare the code, translate the high-level sequence objects into the low-level tensors the model needs. This includes creating the slot mapping, which tells the attention kernel exactly where in the giant KV cache tensor to write the new keys and values for each token. So I guess it's just a slot mapping, it just keeps where the tokens are in the KV cache. Yeah, this prefill. Yeah, because that's what prefilling does. Then they use this trick where they record the computation graphs of the Python during the initialization or the first execution, and then later they just run the model with this graph replay, and this contains pre-computed and compiled computation graphs as opposed to compiling and calculating the Python code again. Then they have this global context, which is like a global memory where model can access some tensors like slot mapping or block tables, as opposed to passing this, it's called prop drilling in React. So I guess maybe here as well, where you need to pass these like through a bunch of different functions and classes to get to where you need them. Instead of doing that, it's just stored in this global memory that can be accessed by anything. Then in the model's Qwen3, there is just this Qwen3 architecture. If you want to use this model, you can use this architecture. Then I asked, where and how is the memory of GPU accessed? So there are four main categories of data on the GPU. Model weights, the static unchanging parameters of the neural network. This is in inference, so this is not training, so they are not changing. KV cache, the dynamic per request key value states for attention. This is the largest and most complex part of the memory management. Input activation tensors, the temporary transient data for a single forward pass. Input IDs, position IDs, hidden state, etc. And then CUDA graph structures, a special cached representation of the model's computation graph for fast replay. This allocation happens in model runner, where we set the device. A command tells PyTorch which GPU this process will use. So that's the rank. Rank is the GPU. And then set default device CUDA. And then self model Qwen3 for causal LM. So that's for the weights. Weights are allocated on the GPU at startup and then populated via a one-time copy from the CPU. They are accessed implicitly by the PyTorch kernels whenever a layers forward method is called. So that's gonna be it for this repository and this learning. I think I will be referencing this again and learning from it further, maybe even making some videos. You can check my other videos on my channel here if you are interested in learning more about AI research and science and engineering, and see you next time.